There's a couple of different directions we could go from this point,
Yeah,
but I want to give some time to your research with EEG and tinnitus,
sure.
because that's, as you've mentioned, that's something that really has fascinated you, and it's such an interesting area, as you say, like a frequency or a sound that has no external sort of
Right,
source, and
right.
yet we can hear it, and that's really fascinating. So can you talk a little bit about your research around tinnitus,
Yeah,
and then we can talk a bit about how you're using EEG to do that research?
yeah, of course. So there's many theories as to the neurophysiology of tinnitus and how it works. I would say right now, and this will change, but right now, the literature and the field seems to agree a bit that there's some sort of peripheral damage that is a trigger for this abnormal percept of sound. And so cochlear damage can be a lot of things. So that's damage to the inner ear. Typically, we think of cochlear damage as hearing loss, which is usually outer hair cell damage. That is a very old viewpoint of cochlear damage. So you can have cochlear damage without it showing up on a hearing test because a hearing test is only testing certain types of neural fibers and their firing. And so you can have damage to the inner hair cells of the cochlea, and we don't currently have a direct way to test that function. Well, we have a few outer hair cell measures. We have measures of the eighth nerve, but we don't have really good measures of inner hair cell firing. So it is possible to have hearing loss that your audiologist might not be able to pick up on unless they're doing other tests. So, other tests that can pick up on hearing loss are otoacoustic emissions, which test outer hair cell function and are more sensitive to subclinical hearing loss. Audiologists typically only test up to 8 kilohertz, and we hear up to 20 kilohertz. And so people are now starting to test those extended high frequencies more to see if there might be damage in that area, but there's no normative data. So we wouldn't be able to say for your age, oh, you have hearing loss here. It might be typical. So that's an interesting area. But all in all, we think there might be some sort of cochlear issue that is resulting in a lack of excitation to the central system. When we have that lack of excitation of neural firing, then what also happens is the inhibitory system does not fire or communicate as well because they're all interconnected. So you can
Mhm.
imagine you might have an excitatory neuron and there's inhibitory neurons connected to it. If that neuron stops receiving input, these guys are also going to stop firing, which then, if they innervate these other neurons that are excitatory, these guys will start being hyper excited because they can't be inhibited. So
Mhm.
that's how we get what's called the homeostasis of the system thrown out of balance. And without going into too much detail, if the homeostasis is thrown out of balance, that puts you at risk for things like tinnitus, hyperacusis, um, these atypical auditory sensations. So we really think it has to do with inhibition. So I had a mentor when I was hired at University of Texas. His name is Craig Champlin. He's a legend. He knew my interest in tinnitus and he suggested to me, why don't you look at something called sensory gating in tinnitus? And I thought, oh, what's sensory gating? And so I did a deep dive, and it ends up that sensory gating is a EEG measure. It's a measure or tool that we think reflects something called sensory inhibition. So it is a measure of inhibition, a very specific type. There's a lot of types of inhibition, but this is a very specific type. It's pre-attentive, meaning you don't have control over it. It's an obligatory response. So we all have it. We don't know we're doing it. And it's really heavily studied in schizophrenia. That's where it really was developed as a tool or a measure of inhibition, and has been linked to auditory hallucinations in schizophrenia, and has been so heavily studied that it is thought of or considered to be an endophenotype of schizophrenia. And we know what genetics contribute to this mechanism. We know the networks, hippocampus, frontal, prefrontal cortex, all that. So it's really well understood, really, really well understood in neuropsychology, but had not been looked at in the realm of audiology or auditory neuroscience. And so I thought, well, if we think inhibition, we don't know what type, but in general, if inhibition might be an issue in tinnitus, maybe this tool or this measure could pick up on that. And so we decided to apply that to our lovely college student population who surprisingly were coming in reporting tinnitus and also seemed to have very normal hearing. So that raised the question of, if we're not picking up on a hearing or cochlear damage, doesn't mean it's not there. Could still be there, but they're at less risk for this peripheral inhibitory decrease being an issue. So maybe there's a central inhibitory problem, and sensory gating could reflect that. It's a very simple measure. It takes about 20 minutes. It's very clinical. You can have the patient read or watch a movie on mute. That's what we have them do because they can't fall asleep. They have to be awake. But we also don't want them paying attention to the sound because we know that affects this response. It needs to be completely subconscious. And so all it is 2 auditory stimuli that are the same, identical. They can be 2 tones. It can be 2 syllables. It can be 2 noise bursts. Clicks are heavily used in neuropsychology. And they just go, we use a tone. It goes beep, and then we wait 500 milliseconds, beep, and then we wait about 7 seconds, and that resets the system. And so you do this over a period of time. You average the brain's response to the first stimuli in the pair, and then you average the brain's response to the second stimuli in the pair. And if you're gating, you've heard the first stimulus, so the second one shouldn't be important to you because you've heard it. So we expect a suppression in the amplitude of the brain's response to that second stimulus. Okay, so it should be reduced. And if you have atypical gating, the responses to both stimuli might be the same, or the response to the second stimulus might be larger than the first. And so that reflects a lack of inhibition, a lack of the central nervous system's ability to suppress or filter non-novel or unwanted information. And so the theory goes that if somebody has poor gating, it could be that they're able then to perceive this internal auditory signal that is usually filtered out. So we definitely don't think this is going to be the mechanism for all tinnitus sufferers. It might be that some people have, due to genetics, have naturally great gating. And so when they get hearing loss, they don't develop tinnitus because they have a good gating system in place. But it could also be the case that for those who do have tinnitus, their gating system isn't great. And so when they get hearing loss, they're naturally inclined to develop tinnitus. We have shown this to be a mechanism in adults with normal hearing. Our work has been corroborated by another group in West Virginia, Kenneth Morse, and his group have shown very similar findings to ours. And so now the next step is to look at this mechanism when hearing loss is present, as well as tinnitus, because those two variables are going to interact on the gating response. But hopefully, if our findings hold, at least in a subgroup of tinnitus sufferers, we might have a way to diagnose that percept.
Mm-hmm. That's really interesting. So tinnitus, still a lot of times the root cause is some sort of hearing damage or trauma. But what your research is suggesting, the theory is that it's a mechanism related to that filter, that inhibition, that gating, that is not functioning as it should, that is creating that perception of frequencies without those external frequencies being present. Interesting.